Hello again, this is Jerry Pinter, and welcome to Chapter 5, Part 2. In this part of the lecture, we will talk about friction and drag. We saw earlier in the course that there are three types of friction. In this video, we're going to look at these in a little more detail. The three types of friction are kinetic friction, static friction, and rolling friction. So kinetic friction is friction due to motion when an object is slipping or sliding on a surface. So the child on the slide here is sliding to the right. Therefore, there is a kinetic friction force pointing backwards, always in the opposite direction, due to the friction between the sled and the ice. Kinetic friction is designated as F sub k, where the k just reminds us that it's kinetic friction. The kinetic friction is going to be calculated as a coefficient of friction called mu. So this is mu sub k for the kinetic coefficient of friction, and we multiply that by the normal force. So we will show that these coefficients here are usually looked up in a table, and they depend on the surface. For example, slippery ice will have a much lower coefficient of friction than rough wood would have. Remember, the normal force points up here, but it's the normal force that determines how much kinetic friction there is. In other words, the heavier an object, the more friction there will be because that normal force will be greater. The second type of friction that we're going to look at is called static friction. And static friction prevents something from slipping. So our frog on the sloped surface here would normally slide down if it was slippery, but because of static friction, it holds the frog up. So the static friction points in the direction that goes opposite to the direction that the frog would slip. So the frog would slip down and to the left. He doesn't because there's static friction pointing up and to the right. Again, it's a similar formula. The static friction maximum value is equal to mu sub s. So this is a different coefficient for static friction. And again, we'll look these up in a table shortly. But again, we have mu multiplied by the normal force n. And in this particular problem, remember the normal force is pointing up at an angle. So it's a little bit confusing at first, this idea of maximum static friction. We will talk about this later in this video lecture when we deal with static friction. The third type of friction is called rolling friction. This again has a similar formula. F sub r, where r is for rolling, is equal to mu sub r times the normal force, n. So if we have a wheel here that's rolling to the right, the rolling friction would point back to the left, and of course the wheel has weight going down and a normal force going up. We will see an example with rolling friction as well later in this video. So all of the equations for friction, whether it's static, kinetic, or rolling, have a similar equation where the friction force is equal to mu, the coefficient of friction, times the normal force. So mu depends on the material. So this is a table from your textbook which has the coefficients of friction for the three types of friction: static friction, kinetic, and rolling. And these are some commonly seen materials. For example, rubber on concrete, that would be used to model a bicycle or an automobile or a truck on a road. So you can see the static coefficient here, mu s is 1.0. The kinetic coefficient is 0.8. And notice the rolling friction coefficient, how small it is, 0.02. This is not a surprise. Remember, the purpose of a wheel is to eliminate friction. And so you can see it has a very small coefficient. There are some other materials here, steel. On steel, whether it's dry or lubricated with oil or grease, we can see that we get a great reduction in coefficient of friction by using lubrication on the surface here. Wood on wood, this is commonly used when we have, for example, a chair or a wood box or crate sliding on a wooden floor. And then wood on snow and ice on ice, here are the appropriate numbers there. We will be referring to this table as we go forward and work some problems. We'll be pulling these these numbers out of here. And this is not something that you memorize, but it's just a reference that you use to look up when we need the coefficients. So let's start with an example of using kinetic friction. So we're asked to calculate the force required to slide a 50-kilogram wood crate across a wood floor at a constant speed of 1 meter per second. So here is our picture of what's going on here. We've got the woman pushing this big wooden crate, and she's going to slide this thing across the floor. So in order to make sense of what's going on here, let's go ahead and construct a free body diagram for the crate here. In the vertical direction, we have the crate's weight force pointing down, as always, due to gravity. The floor pushing up on the crate is the normal force here. We have the woman's pushing force pointing to the right, that's P, and opposing that, because the crate, remember, is sliding to the right, the kinetic friction force is pointing back to the left. And this is kinetic friction, because remember, kinetic friction has to do when something is actually moving or slipping or sliding. Now, notice that we're told that the crate is moving at a constant speed of 1 meter per second. So what that means to us is that this is an example of dynamic equilibrium, meaning that the net forces have to add to zero because there is no acceleration here of the crate. So in the y direction, in the vertical direction, the forces have to add to zero. So these two forces, the normal force going up and the weight down, have to cancel each other. All right, so normal force minus weight is equal to zero. In other words, the normal force is just equal to the weight, which is mg. All right, we'll plug in some numbers later. Now, in the horizontal direction, also we have equilibrium because this crate is moving at a constant speed. So we're going to add our forces and set them to zero. So we have the push force going to the right minus the friction force, because it's pointing back in the negative direction, is equal to zero. Now remember, kinetic friction is equal to mu sub k times the normal force. So we're going to go ahead and substitute that in for F sub k. We can solve now for the push here. Remember, we're trying to calculate how much force she needs to slide this crate across. So we're solving for P. So from this equation here, you can see that P is just equal to mu sub k times n. And remember, the normal force over here is equal to the weight of the crate, which is mg. So her push is mu sub k. Now we have to look that up in the table. So if we go back to the table, you'll see that wood crate on wood floor for kinetic friction has a coefficient of friction equal to 0.2. So that's where I got that number right there. The mass of the crate is 50 and G is 9.8. So we just multiply these three numbers together and we get 98 newtons of force is what is required to slide this crate across the floor. Let's now turn to static friction. Static friction prevents an object from slipping. So here's our woman again. Imagine now she's comes into the room and she wants to push this crate, and it's a really heavy crate. So she starts pushing on it very, very softly or gently at first, and nothing happens. Okay, the same thing happens if you try to push your couch across your floor of your living room. When you first start pushing it, nothing happens. So what do? Well, you start pushing harder and still nothing happens. And you keep pushing harder and harder and harder. And then all of a sudden the crate will start to slide. Okay, so I'm going to go ahead and run the demonstration here, the animation that is. So notice she's pushing, nothing happens. And now all of a sudden it starts to slip and go across. All right, so what is happening here? Well, static friction, first of all, always opposes the direction of intended motion. So if she's trying to push this crate to the right, the static friction force is going to push back to the left. So here's a sort of a free body diagram of our crate. Her pushes to the right, static friction opposes that and pushes back to the left. What's interesting about static friction, though, it's not a constant force. It's a variable force that matches the applied force. Because remember, static friction applies when the crate is at rest, like right now, before it starts to move. So what happens here is, if we can show this in a graph, this is on the horizontal axis of this graph is the amount of her pushing force, let's say in newtons. The vertical axis is the amount of the friction force in newtons. So notice there is a straight line here with a slope of 1. So what does that mean? Well, if she pushes with 10 newtons of force, the static friction opposes her with 10 newtons of force. If she pushes with 20 newtons of force, let's say right here, the static friction then opposes her and pushes back with 20 newtons of force. Therefore, nothing happens. The object does not slip or slide until we get up to a maximum point here. This is the maximum value of static friction, which is given by the formula mu sub s times n. What happens when we reach that maximum is all of a sudden there's not enough static friction to hold the object still anymore, and now the object starts to slide. And notice what happens when we exceed that maximum force. The kinetic friction actually drops down a little bit. What this means is that the kinetic friction force is always less than the maximum static friction force. And again, this is something that you can observe at home very easily. You can take something on your desk, for example, something kind of heavy, maybe a book, a heavy textbook, or maybe a heavy jar or can of food, or even your laptop or your tablet. If you start pushing on it real gently with your hand, notice it kind of sticks to the table. And then all of a sudden, it will start to move. But once you get it moving, it's usually easier to push it. So in other words, it's easier to keep it going down here than it is to get it started up here. It takes less force. So this shows up in the coefficients of friction. Mu sub k, the kinetic coefficient of friction, is always less than mu sub s. And you can see that by looking back at that table that we showed earlier. The mu k values are always lower than the mu s values. All right, so let's go ahead and do an example now with static friction. So the question is, how much force you need to push with to get a 100-pound, which I converted here to 45.5 kilograms, box moving. All right, in other words, how much force is required to get this box to start moving, to start slipping across the floor. Assume both the box and the floor are made of wood. So again, here's our free body diagram. It's the same as the last problem. We have the push to the right, the static friction force back to the left, opposing. We have weight down and normal force up. So as you begin pushing against the box, static friction pushes the box in the opposite direction with equal force because we're in static equilibrium, right? So if you're pushing with 50 newtons and it's not moving, that means the static friction force must be 50 newtons as well, pointing in the other direction. The box only moves when you exceed the maximum static friction force. So what is the maximum static friction force? Well, that is F sub S max, and it's given by mu sub S times N, the normal force. So mu S is something, again, we find in the table. So if you look up wood surface on wood surface for static friction, you'll find that the coefficient mu sub S is equal to 0.5. So that's our number right here. The mass of the crate was given as 45.5 kilograms, and G, of course, is 9.8. So multiplying these three numbers together, we get a force of 223 newtons. And by the way, 223 newtons, if you do the conversion here, if you divide it by 4.5, you will find out that this is 50 pounds of force. All right, so that's in the English units, you have to push with 50 pounds. Now notice the numbers here. The crate weighed, if we use English units, the weight of the crate was 100 pounds. So the normal force of the floor on the crate is 100 pounds. Remember, the coefficient is 0.5, which is 1/2. So the maximum force of friction is 1/2 the weight. And that's where we get the 50 pounds of force needed to slide this crate. Let's now take a look at a more challenging example of static friction. This is a pretty standard and common problem that is seen again in almost any introductory physics class. It's the idea of at what angle does something start to slip? So in this particular problem, we have a 50 kilogram steel file cabinet here, and it's on the bed of a dump truck, which is also made of steel here, the steel bed. So it says the bed is slowly tilted upwards. At what angle does the cabinet start sliding? So obviously, as we make theta here, the angle larger and larger as this thing goes steeper and steeper, at some point it's not going to stick anymore, and static friction will not be sufficient to hold it up, and it's going to slip and slide off the back of the truck. So to solve this, let's start with a free body diagram of the file cabinet here. Okay, now what makes this problem difficult and a bit challenging is just the fact that we have to deal with vectors at arbitrary angles. And remember, our strategy whenever we have vectors involved is always to break those vectors up into components, because we can easily deal with the components. The hard part is just breaking or decomposing the vector into the components along the coordinate axes. So what we've done in this problem is it makes sense to align our coordinate system tilted with the bed of the truck. So notice our x-axis is drawn here. It has the same angle theta that the bed of the truck has. And likewise, our y-axis is perpendicular, as always, to the x-axis, so it goes at an angle as shown. The reason we're doing this is somewhat similar to what we did in an earlier chapter, I believe it was chapter 3, when we dealt with motion on a ramp or a slope. We used this same trick where we used a tilted coordinate axis system in order to solve the problem. So what we can do now is label the forces acting on this file cabinet. Well, we always have weight or gravity, which remember always points straight down. So that's our vector right here, weight W, which is equal to mg, the mass times g for the file cabinet. The normal force, remember normal force always points perpendicular to the surface, or normal, that's what normal means. So the normal force is going to point up along our tilted y-axis as shown here. The other force, of course, is static friction. The reason this doesn't slip off the truck is because of static friction. So normally the file cabinet would want to slide and slip down the slope in this direction. So static friction must point up the opposite direction. It is the opposing force here. So these three forces comprise our free body diagram. Now, what we're going to need to work with, though, are the components of these forces. Now, the nice thing here about our tilted coordinate axis is that the normal force points along y, and the friction force points along x. So we don't have to do anything with them. The one we have to deal with is the gravity force, weight, pointing straight down here. We have to decompose the weight into the x component pointing along the ramp and into its y component, which points down in this direction along the y-axis. All right, so we will do the trig necessary for that as we go through this problem. So the physics here is that the cabinet will start to slide when the maximum force of static friction is exceeded by the weight component along the x direction. So in other words, when this force here, W sub x, that is the weight component pointing down the slope of the ramp or the bed of the truck. When Wx is larger than our maximum static friction force here, then it's going to win the battle, and it's going to cause the file cabinet to slide down. But when Wx is less than the maximum force here, it's going to stick. Okay, so that's what determines when it goes. So let's go ahead and break this problem up into the two directions. Let's look at the y direction first, which remember is this direction along the y-axis. So this is an equilibrium problem. Right up to the point where it starts to slip, everything is in equilibrium because nothing has moved yet. So we're going to do that right up to the maximum point. So we have the sum of the forces in the y direction is 0. Normal force points in the positive direction. the weight sub y, the y component, is in the negative direction, so we subtract it. So n minus w sub y equals 0. Therefore, the normal force right here is equal to the y component of the weight, which is mg cosine theta. Now, how did I get this? Well, remember this hypotenuse of this right triangle right here. Here's a right triangle. The hypotenuse is here, and it's equal to mg. So this side over here, remember, this is the adjacent side, because here's our theta. This side here is equal to the hypotenuse, mg, times the cosine of theta. Now let's go over to the x components. In other words, the components in this direction along the slope of the truck bed. So in this direction, we see we've got two forces. We've got the W, the weight x component, pointing in this direction down. So to the right, I'm calling that a positive direction. Even though it's down, it's in the positive x direction. So I've got W sub x minus the static friction force, and we're going to use the maximum value of that because that's where this thing starts to slide. So W sub x minus Fs max equals 0. Wx, the x component, that's just equal to mg sine theta. Remember, this side over here was mg cosine theta. This side of the triangle, which is the same as this side drawn here, is equal to mg sine theta. And then from that, we subtract the maximum static friction force, which is mu sub s times the normal force. Now, the normal force, n, we found over here to be mg cosine theta. So I'm going to substitute where I see n right here, I'm going to put in mg cosine theta. All right, and so all of this is equal to 0. Now, notice in both terms, I have an mg here, and I have an mg here. So I can divide everything, all three terms, on the two on the left and the term on the right, which is just 0, divide them by mg. So now it cleans up a little bit. I end up with sine theta minus mu cosine theta equals 0. All right, so let's go ahead and move mu cosine theta to the right side. So I get sine theta equals mu sub s times cosine theta. And I'm going to go ahead and solve for mu sub s. Mu sub s then is equal to sine theta over cosine theta. You might remember from your geometry class, if you studied trig, that the sine of an angle divided by the cosine of the same angle is equal to the tangent of the angle. So sine over cosine is equal to tangent. So we have mu of s is equal to the tangent of angle theta. Remember, theta is this angle up here of the bed. We are trying to figure out what is theta. So in order to solve for theta, we are going to say theta is equal to the inverse tangent or the arctangent of mu s. And finally, we can plug in mu s. We were told that this is a steel file cabinet on a steel surface. So from the table, if you look up steel on steel, dry, no oil or whatever, for static friction, you'll find that the coefficient is 0.8. So that's this number here. And on your calculator, be careful, make sure you're doing the inverse tangent of 0.8. You'll get 39 degrees. So that is our answer. It would start to slip at a 39-degree angle. Now, what I'm going to show you next is a video demonstration where we're going to kind of work backwards, and we're going to take a board, a piece of wood, and put another piece of wood on top of it, and we're going to find out what angle it starts to slip at, and we're going to use that to figure out what the coefficient of friction is for the particular type of wood. So we're going to use this result here. Mu, static friction mu, is equal to the tangent of the angle. So I hope you enjoy the video demonstration. Hello, so in this video, we're going to look at static friction. So one way to demonstrate this, as we just saw in the problem that we worked, is by using a ramp. And so I've got a wood board here for a ramp, and on top of the board we're going to place another wood block on top of that. And if we have the ramp just slightly inclined like this, you can see that the wood block doesn't slip. So in other words, the static friction is sufficient to prevent the gravitational force from sliding it down the ramp. But as we increase the angle more and more, we'll get eventually to a point right here where it begins to slip. So what we can do here is use this experiment to come up with a measurement for the coefficient of static friction for this wood board and the wood block. So what we're going to do here is, first thing, let's take some measurements. We can measure the length of our ramp here is measured at 31 inches. And what I'm going to do is place our ramp right here, and I'm going to increase our angle a little bit at a time until we start to get slippage. And we'll record that height, and then later we can figure out the angle, and from that we can determine what the coefficient of static friction is. So I'm going to start increasing this up very slowly like this, and just watching for the point where it starts to slip. It's right there. And the height there of the ramp is 13.5 inches. So we'll go ahead and use that number to calculate our angle. In the video, we saw that for the wood block, or I'm sorry, the wood ramp here was 31 inches, and the height at which it started to slip was 13.5 inches. So we can use that with our right triangle trigonometry to quickly figure out what theta is. So theta is the inverse sine. Remember, that's the opposite over the hypotenuse. So we have 13.5 over 31, which is 0.435. If we take the inverse sine of that, we can calculate the angle here to be 25.8 degrees. This is a more accurate way than trying to measure this angle using a protractor. All right, so we know our angle is 25.8. So remember that mu sub s, the static coefficient of friction, is equal to the tangent of theta. So on our calculator, we just have to take the tangent of 25.8 degrees, and that turns out to be 0.48. So let's take a look at our table here and see how close this is to what's in the table. So if we look at table 5.1 here, and we find wood on wood right here, we notice that the static coefficient of friction is listed at 0.5. So you can see we're very close to that. We're within just a few percent. And obviously this coefficient here will depend on the type of wood, how rough the wood is. For example, if we sand it really smooth, it's going to have a lower coefficient of friction. If it's rough and bumpy, it'll have a higher coefficient of friction. But nonetheless, you can see that we came up with a value that is very close to that as listed in the table. So next, let's take a look at an example of rolling friction. So ignoring air resistance, what force is required by the engine of a 1,500 kilogram car to keep it cruising at 10 meters per second? All right, so we have our car that's cruising along at a constant speed of 10 meters per second. We can go ahead and draw the free body diagram for the car. We have weight down, we have normal force up, we have the engine force, which is pushing the car forward, okay, by turning the tires and so forth. And then the car, we're going to ignore air resistance here. We're not going that fast, so it's probably not a huge a factor yet at 22 miles per hour. But we are going to try to figure out what this rolling resistance is here. That is the friction force. And remember, the car is moving at a constant speed, so we have a condition of dynamic equilibrium, no acceleration. Thus, the sum of the forces must be 0. So let's go ahead and start in the y direction. Well, the car is not moving in the y direction. So remember, a shortcut here is we know the normal force has to just be equal to the weight, which is mg. So here's our forces in the y direction. Normal force is equal to mg. In the x direction, we have these two forces. We have the uppercase F is the engine force going to the right, and we subtract from that the rolling friction force, F sub r. And those have to add together to be equal to 0. So we have F minus mu sub r times the normal force. Remember, this is the rolling friction force, is mu times n. And that all is equal to 0. The normal force we found over here was equal to mg. So the engine force required is equal to mu times mg. So for mu, you'll have to go and back to the table and look up rolling friction for this would be a rubber tire on cement. All right, and you'll find that the coefficient of friction is 0.02 multiplied by the mass of the car was given as 1500 and g is 9.8. We end up with a engine force required to be 294 newtons. In this last part of this video, we turn to the drag force. Drag is air resistance or wind resistance, and it's very similar to friction. It opposes motion. Drag is caused physically by air molecules striking the object as it moves through the air. So, if you're ever on your bike, you can feel the air striking your body as you ride, especially at faster speeds. Or if when you stick your hand out the window of a car when you're moving fast, you can feel that wind resistance pushing back on your hand. And it's caused from all the microscopic collisions of the air molecules striking the surface of the object. So we're not going to derive this result here. It requires a bit of fluid dynamics, which is beyond the scope of this course. But the result is shown here. The drag force is approximately equal to, so again, this is just an estimate here, 1/4 times, this is a Greek letter rho, which represents the density of air. Now this works for other medium too, for example, denser gases or even liquids. But we're going to just stick to air here. So we're going to plug in the density of air, which is 1.22 kilograms per cubic meter. A here is the cross-sectional area of the object. We'll see how that comes into play. And then the other important thing here is the speed of the object, and notice that it's squared. So this means that larger objects will have more drag force, all right? That's A, the area of the object. And also, the faster something goes, the more the drag force is. And you've certainly experienced this when you're on a bicycle or in a car. The faster you're moving, the more drag you feel against your skin. So in order to calculate drag, we have to figure out the cross-sectional area of the object. What this means is basically we're taking a slice of the object through its thickest part along a plane that faces the wind. So if we have a soccer ball flying through the air, basically we can think of slicing this ball with a, like an imaginary knife right through like this, and obviously the slice is going to be a circle, and the area here would be very easy to calculate as pi r squared. It's much more difficult when we're trying to calculate the cross-sectional area of something like a person on a bicycle. And in this case, we can only kind of do estimates. That's the best we usually can do without putting too much effort into it. So we could, for example, we could draw a rectangle, something like this, around the image here of the cyclist, and then calculate the area by width times height. And this would give us a rough estimate of the cross-sectional area of this cyclist. One of the interesting concepts that comes about when we talk about drag and wind resistance is this idea of terminal velocity. Terminal velocity is basically an object that has reached dynamic equilibrium. So remember, dynamic equilibrium means an object is in equilibrium, meaning all the forces are balanced. It is no longer accelerating, but it is moving. So terminal velocity or terminal speed is the maximum speed of a free-falling or downhill object due to air resistance. So once an object reaches terminal speed, it continues falling at that same speed until it hits the ground. So in other words, instead of an object continually accelerating all the way to the ground, like we worked with before in this course, when there's wind resistance taken into account, the object will eventually slow down and reach a maximum speed, at which point it doesn't speed up anymore. Okay, in other words, the acceleration slows down and goes to zero, and we end up just with the object falling at a constant speed. This is called the terminal velocity. So when an object starts falling, the drag force increases as the speed increases. Because remember, the drag force here is proportional to v squared. So when you first start falling, when an object first starts to fall, its velocity is zero, or very low at least. And as a result, there's not much drag force. But once the object starts to accelerate and pick up speed, then what happens is the terminal speed occurs when the drag force reaches the force of gravity, or the weight, at which point there is no net force. We're in dynamic equilibrium and no further acceleration. So here we have a skydiver, all right, and this person has jumped out of the airplane. Notice the parachute's not open yet. So this person's going to start falling and accelerating at g, 9.8 meters per second squared. However, the wind, as this person falls faster and faster, the force of the air resistance, in other words, the drag force, increases until the drag force actually balances his weight, the force of gravity. Now these two forces are exactly equal to each other. They are balanced. That means there's no net force on this person anymore. So this person is not going to accelerate anymore. He's just going to fall at a constant speed, which is called the terminal velocity. So how do we determine what the terminal velocity is? Well, it's simple. In this picture here, we see that terminal velocity means these two forces are balanced. So the drag force is just equal to the weight force. So remember, drag is 1/4 rho a v squared, and weight is mg. So we can just solve this for the velocity here by moving all this stuff over to the right side and square rooting. So we get terminal velocity is approximately equal to the square root of 4 mg over the density of air, that's the rho there, times the cross-sectional area of the object. So this is for a free-falling object that's falling directly down vertically. Now, what we see here in this equation are two things that affect the terminal velocity. Assuming, we're on Earth, so g is 9.8, and assuming we're falling through the air, which, we'll just assume it has a constant density of 1.22. The only things that can change here are the mass of the object and the area of the object. So the more heavy the object is, in other words, the greater its mass, the greater its terminal velocity will be. Likewise, if we make the area larger, well, the area is down here in the bottom of this fraction, so larger objects are going to fall slower. So this is how a parachute works, right? When this guy opens his parachute, it's going to increase his effective area by a large amount. And so by making A much larger down here, that's going to have to slow him down by an equally large amount here. This is square rooted, but the idea is the area is down at the bottom here. So the bigger we make the area, the slower the person will fall. In the next couple of minutes, you'll get to see a terminal velocity video demonstration where I'm going to be dropping various objects and comparing their speeds while falling. And we'll, while we do the experiments, we'll make note of the differences in the mass between the objects. One might be heavier than the other. And also remember the area of the objects, because the area and the mass are the two factors that determine the terminal velocity of a falling object. So we learned in the lecture that the terminal velocity of an object that's falling depends on two things: its mass and its cross-sectional area. So here I've got a couple objects that actually have fairly similar areas. A coffee filter here, and this is a 3-pound weight, but obviously their masses are very different. So they should have extremely different terminal velocity. So let's go ahead and drop these, watch them fall. All right, so the coffee filter, of course, falls very slowly because it has two things going against it. It has a very small mass and it has a relatively large area compared to that small mass. So one thing we can do, and we did this earlier in the course, is we can reduce the area of the coffee filter by crumpling it up into a little ball and making it as small as possible to reduce its cross-sectional area, like that. So let's try it again and see how it compares now. So that time you could see that they actually fell together with apparently about the same speed. So by reducing the area of the coffee filter, we were able to eliminate the wind resistance and the drag. Let's do another experiment here with a couple of balls I have here. We've got a beach ball and a basketball. So which one do you think will hit the ground first if we drop them? Do it one more time. So as you probably guessed, the basketball fell faster. And there's two reasons for this. Again, the basketball has more mass than the beach ball. And also, the beach ball has a greater cross-sectional area, so it has more wind resistance, more drag, and that slows it down as well. For our last one here, we're going to drop, this is just a lid of a storage container, and we'll drop that at the same time as our 3-pound weight. So again, as you probably predicted, the 3-pound weight fell faster, and the reason for this, of course, was wind resistance again. This light lid here has very small mass compared to the steel weight, and in addition, it has a large surface area. So one thing we can do is, let's keep the surface area the same, but we can add some mass to it. So I'll put a couple of blocks on top of the lid, probably not as much mass as this weight, but we'll see if it's enough to compensate the effect and cause them both to fall at the same speed. Looks like they fell pretty close there. So that's our demonstration on terminal velocity and wind resistance. Our last slide here in this video is another example. This time we're going to figure out the terminal speed of a bike going down a sloped hill here. So we're given that the total mass of the cyclist and the bike is 80 kilograms. The slope of the hill, theta here, is given as 15 degrees. And we'll assume that the cyclist's cross-sectional area is 0.75 square meters. So remember that terminal speed means no acceleration. This is a dynamic equilibrium problem. So here is a, our cyclist, and we can sort of turn this into a free body diagram. The cyclist's weight is pointing straight down. The normal force is pointing up and to the right. And then we have drag force, wind resistance, pointing back, opposing the motion. And we're also going to include rolling resistance in this problem, which also opposes the motion. So what we're going to do here is we're going to tilt our X and Y axes again along the slope of the hill. So the positive X direction is going down the hill, and then Y comes up at a 90-degree angle to X like this. Remember, weight is straight down, so we're going to decompose the weight into the X component here and into the Y component here when we go ahead and do the equations here. So in the X direction, we have the sum of the forces is equal to 0. So we have to look at our diagram here. In the X direction, notice we have the weight force, X component, W sub X, pointing along the X direction. So that's why I listed that first. And then in the opposite direction, in the negative X direction, we have drag and rolling resistance. So I'm going to subtract D and I'm going to subtract F sub R, and all of that has to equal to be 0. So the X component of weight is mg sine theta, which is similar to what we did in the previous problems by using the trig here of this right triangle. Drag is 1/4 rho AV squared. Rolling resistance is mu R times the normal force, and that is all equal to 0. Let's see, next thing I'm going to do here is we want to solve for velocity. So let's, the term with velocity is right here because I have a v squared. So I'm going to move this by over on this side by itself and rearrange this equation, basically, being careful to flip the signs where I need them. And so I have 1/4 rho AV squared equals mg sine theta minus mu n. Now at this point, I need to figure out what my normal force here is. All right, we're not, given that, of course, but we can figure that out. Notice that the normal force pointing up in this direction is pointing up along the y-axis. That has to balance this force here, the y component of the weight, because the bike is not moving in the y direction. It's only moving in the x direction, which is down the hill. So in the y direction, we have an equilibrium problem where the normal force minus this y component of weight is equal to 0. And the y component of weight is mg cosine theta. So the normal force is just mg cosine theta. So I'm going to substitute this expression here for the normal force into this n right here. Okay, now you can see it over here, the mg cosine theta. And then I'm going to solve for v by multiplying everything here by 4 to get rid of the 1/4, dividing by rho, dividing by a. So here's all the math in here, all right, the algebra. And then, of course, that's v squared. So we have to take the square root of all of that to get v. So finally, I have an expression here for our terminal speed of the bicycle. The next step is just to plug in all our numbers. The mass was given as 80, g is 9.8, theta was given as 15 degrees, and over here, the rolling coefficient, I assumed rubber on cement, which is 0.02. Again, m is 80 kilograms, g is 9.8, theta again is 15 degrees. And then down on the bottom, remember rho is the density of air, which is 1.22, and the area we were assuming 0.75. And I didn't put the units in here just to save some space, but everything is in the proper meters, kilograms, second units, or SI units. So when you do the math here and the dust finally settles, we get our answer, which is 28.7 meters per second. That converts to about 64 miles per hour. That's it for this video. I'll see you in part 3.